All right, let's get started. Got my sign-in sheet, and I'm going to start passing around. I'm curious how many brought their laptops today. I mean, it's not absolutely completely necessary, but we are going to sort of briefly look at some stress-strain curves today. I've got everything here set up to do this on Excel on the screen. I messed around with the font settings a little bit on Excel so that the font on the formula bar and whatnot shows up real big so that you all can read it. A couple quick announcements. Don't forget that you all have your first homework assignment due next Tuesday. Right now, you should be equipped to do, I think, every problem on the assignment except the last one. And after today, you'll be able to do the last one. So you'll have plenty of time to do the assignment. I want to show you what I've done on Blackboard. So first off, your attendance from last week, I went ahead and uploaded that. And then I also added some grade columns just to show you what I've done. So I'm here on the Blackboard page, and I've got student preview mode on. So this should be what you see when you look on the page. If you go to My Grades, there's obviously nothing here, but I put in all of the assignments. So this is everything for the semester. Now the only one that's showing up with any weight is homework number 1, because that's the one you all have right now. As the assignments get created, I'll add more points and whatnot. But again, try and keep a running total of everything that's going on throughout the semester. All right, sound good? Okay. All right. So today, what I want to do is I want to try and tie up the fundamentals that we've been talking about. If you recall, we've spent last week sort of defining 2 fundamental concepts in this class, and that is what is stress and what is strain. And basically, in a nutshell, stress and strain are 2 quantities that we use to sort of remove geometry from the equation of from the situation. If you're looking at a steel bolt or a steel column or a steel drive shaft or what have you, by dealing in concepts and stress and strain, you're removing the geometry. It doesn't matter if it's a steel bolt or a steel beam or a steel drive shaft or what have you. By employing stress and strain, we're looking at the behavior of steel in those regards. Well, in order to characterize materials, how does steel behave, how does aluminum behave, how do plastics behave and whatnot, we need to look at the relationship between stress and strain. And so at the end of class last time, I showed you all a video involving a tension test. The tension test is by and large the most fundamental materials test or test that we do in engineering, period. And the long and short of it is we take a specimen of a given material of a standard size, and there's a number of different sizes that you could use. Depending upon whether or not you all are civil or mechanical engineers, at some point you'll do a tension test in one of your courses. So you won't do it in here, but you will do it at some point. If you're in mechanical, you'll do it in Engineering 215. If you're a civil, you'll do it in CE 321. You take a specimen of a standard size, and now over here on the right, these are concrete specimens. So with concrete, you wouldn't apply tension, you would apply compression, you would push on them. But the idea is you take these specimens and you load them at a controlled rate and record their response. And by having a precise knowledge of the geometry of these specimens, we'll be able to record load and deflection data from the test. We can convert that pretty easily to stress-strain data, and we'll generate what's called a stress-strain curve. And the nice thing about stress-strain curves is that stress-strain curves are unique to a given material only. And so what I mean by that is if you have let's say we're talking about structural steel. Whether you have a steel specimen that's, let's say, really small or a steel specimen that's really large, by normalizing everything into stress and strain, you can get the same curve every time. In other words, steel is always going to behave the way steel is going to behave. You're always going to get the same stress-strain curve, and that's why they're so relevant. So I'm not going to play the video again. We watched that last time. I want to take these stress-strain curves and sort of break them apart and look at their anatomy a little bit and look at their different characteristics and their different important points and what have you. The one thing that I do want to mention, though, is that if you look at the results of a typical tension test, different materials are going to give you different stress-strain curves, and that's sort of the whole point. So like for instance, you can clearly define some very separate regions, let's say for a low carbon steel, but if you're looking at something like an aluminum alloy, it just behaves a little differently. So I'm going to today try and characterize that behavior a little bit. We'll have some example calculations to go along with that. I want to try and characterize material behavior by looking at a particular stress strain curve. So I want to start to digest the stress strain curve for steel, for structural steel. And this is probably one of the common stress strain curves that you will review in engineering, period. The stress strain behavior of structural steel is sort of something you can set your watch by. It's always going to be the same, assuming that your steel meets the specs. If you look at this stress strain curve, there are a series of regions. We have a linear region, what's called a perfect plasticity region. We have strain hardening, and I kind of want to define what each of those regions are and what they mean. Now, before we do that, I want to sort of clarify one thing. The curve that you're seeing right here is a little bit out of scale. Some of the regions have been exaggerated so that you can visually see what's going on. And to explain that, I think the easiest way to do that is to use the analogy of a football field. So I have a feeling everybody in here knows what a football field looks like, end zones, 100 yards, so on and so forth. Okay, so imagine that I've got a football field here on the screen, okay? And let's say that I've got an end zone, right here, and I have an end zone right here, right? So here's the football field down below, okay? So if you want sort of a visual representative scale of what this really looks like, this point right here, that's about the 1 yard line, okay? This point right here, that's about the 10 yard line, okay? And then everything else is everything here. So if I drew that to scale, this linear region would seem like really, really tiny. You'd have a little plateau, and this thing would be stretched out like crazy, okay? So this image is a little, it's like schematic in nature. It's not, perfect to scale. But, one thing I will point out, if you look, if you try and visualize this with a little bit of, dimension to it, like if I were to try and draw it out for real, it'd probably look something like this. Like it would probably, it'd probably go up like that, and then it would, go like that. Maybe something like that. That would probably be a little more realistic. One of the things that's nice about using steel in engineering applications is steel is a material that is very highly ductile. Now ductility is something that I'm going to loosely define now, and I'm going to come back to it later, but steel, in a nutshell, has the ability to withstand a lot of deformation. Like it can deform quite a bit before it fails. And so that quality is a loose definition of ductility. I'll have a more precise one here in a little bit. But I just want you to keep that in mind. It's one of the reasons why steel is so commonly used in engineering. All right. Let's talk a little bit about the behavior, and I want to sort of separate these into given regions. So we have, like these points like O, A, B, C, D, and so I'm going to sort of separate these into individual regions and sort of explain what's going on. Now, for most engineering applications, probably the most important region, or at least the region that we try and restrict the behavior to the most, is this first region, this OA. Okay? Now, this is a linear region, and for steel, there's another name for this. We call this the elastic region. Okay? Now, here's what this means. Now, remember, this curve is representing like physical behavior. Now, if I take this material and I load it, I yank on it, this is how it responds. Okay? Now, the reason why we call this first region the elastic region is because it behaves just like that. It behaves a lot like a rubber band. Okay? Imagine if I had a rubber band in my hand. Okay? Now I have this rubber band, and I take it and I pull on it a little bit. I stretch it a little bit. What happens if I take that rubber band and I let it go? What does the rubber band do? Snaps back. It snaps back to its original shape. Okay? What's happening in this linear region is exactly that. So I've got this piece of steel, and I yank on it. And if I yank on it in its linear region, what happens is this. I yank on it, and it stretches. But if I let it go, it snaps back to its original location. More often than not, we really like elastic behavior in engineering applications. I mean, if I take a look at this building, okay, there's floor beams in this ceiling right here. And so there's a classroom, or there's offices above here, and there's people walking on those offices, right? There's load being applied to these floor beams up here, okay? This is physics. You put load on these floor beams, they are going to deform, okay? I would prefer that those elements remain elastic. In other words, when those people leave the room, they snap back to their original location, okay? If not, if they don't behave elastically, then the flip side is that they behave what we call plastically. So there's elastic behavior and plastic behavior. And plastic behavior is a lot like a Coke can. You know, if I have a Coke can in my hand and I crush it and I let it go, it's not going back to a perfectly smooth Coke can. It's going to remain crushed, right? So imagine if something like that happened with these floor beams up in this floor system. You know, people walk on it and they remain sagged, right? Then you put more load on it, they sag more. That the building is not behaving the way that we want it to, right? So in most cases, we like elastic behavior. So in design scenarios, you're going to see us refer to elastic behavior quite a bit. And that's why we want, our systems, once they unload, to go back to the way they were. It makes the behavior more predictable and what have you. Now, let me be clear. That's not always the case. There are some instances where we prefer inelastic behavior. There are some very specific instances. Bless you. So, like one instance is, for instance, in vehicle design. If you were to design a vehicle to perfectly survive a car crash, you have a car and it runs into a brick wall and it comes out without a scratch on it, okay? First off, if you wanted to try to design a car like that, good luck. Not going to work, okay? But second, from a safety standpoint, that actually doesn't work very well. Because if you're driving a car and it runs into this brick wall, if that energy from that crash is not absorbed by the car, guess where it's going? It's going to you. So goodbye you, okay? So one of the things that we do in automobile design, particularly when we're looking at the frame or the body of the car that frames the car together, we purposefully design what we call fuses in engineering. And specifically, there are regions of the car that are meant to plastify, that are meant to deform, that are meant to absorb all that energy, so that energy doesn't get absorbed to you. Okay? So it's like, you have a car crash and the car looks mangled, but if you're fine, then you did a good job. So that's sort of the point. We do the same thing in civil engineering when we're designing buildings and seismic applications. When you have a building that's subjected to a really large earthquake, as structural engineers, we don't care if the building has to be completely rebuilt from the ground up, just as long as at the end of the earthquake nobody died. And so when you look at some of the forces that are generated from earthquakes, there's no way to design a building so that it would remain perfectly intact and elastic all throughout an earthquake. So you start selecting elements in the building and say, I want those elements to fail before everything else does. So those are some specific instances, and plus I just figured I'd throw some cool stuff at you. But in most applications, we're going to keep everything elastic. Now, for a lot of, for most engineering materials, that elastic region is either linear or we can assume it to be linear. So if I look at this region, there is a relationship between how much load you put on the system and how much it deforms, okay? And like I said, we can assume that to be linear. So if you ever hear the term Hooke's Law, Hooke's Law is basically saying that we are assuming that materials behave linearly, that there is a relationship between how much stress you put on something and how much strain you get. And that relationship, or the slope of that line, is a constant that we call the elastic modulus. And a lot of times in engineering, you'll hear it referred to as Young's modulus, okay? Now, Young's modulus is a particular parameter that is unique to given materials. Every material has a unique Young's modulus. So steel has a Young's modulus. Aluminum has a Young's modulus, so on and so forth. So when you're doing an engineering problem, you need to understand two quantities. You need to understand the geometry, how deep is that beam, how long is that torsional shaft, and so on and so forth. You also need to understand the behavior of the materials. If it's steel, what is its Young's modulus? What is its yield stress? And so on and so forth. And so this quantity E is a very important quantity for us to understand. So if you go to Appendix I in the textbook, there's E values for all sorts of different materials. So I'd recommend just sort of checking it out. Now, let's talk about what happens when you keep applying load. So I'm going to sort of tell this as if it's a story of this tension member and it's starting to stretch. Okay. So I don't want this to turn into a massive chemistry lecture or get into, you know, crystalline structures of whatnot. That isn't the case. But I do want you to kind of have a general idea of what I'm talking about here. So, you know, if we're starting to get into chemistry land and into crystalline structure land, I mean, steel is an alloy. It is a crystalline structure of you know, molecules and whatnot bonded together. When you're taking this tension member and you're loading it, okay, and you're stretching it, those bonds are stretching as well. And there's a point when those bonds begin to break, okay? And what happens is you start to get to a point where it begins a process called yielding, okay? And I have an example to sort of, I think, physically or, you know, mentally explain what's going on with yielding. I think it's the easiest way to explain it. It's a little gross, but imagine if you had a piece of chewing gum in your hand, okay, and you have the piece of chewing gum and you start to pull it. You know, right as you start to pull it, the gum is kicking back a little bit, like it's resisting you. But there's a point once you pull it that it just sort of goes. It just sort of freely deforms, right? That to me is the easiest way to explain what's going on with yielding. There's a point when you're starting to break those structural bonds in the metal and it just starts to freely deform. Now in metals, we have a name for that. It's called the yield stress. It's when the metal begins to yield and those bonds begin to break. When you're looking at, let's say, structural steel, one of the things about structural steel, every grade of structural steel has the same Young's modulus. It has the same slopes. But different grades of structural steel have different yield stresses. So like A36 steel has a yield stress of 36 KSI, whereas A992 has a yield stress of 50 KSI, and so on and so forth. So that's where you can see differences in grades of material and how they behave. Generally, the linear region is the same, at least for steel. The linear region, the Young's modulus is always going to be constant. Again, it's another one of those things you can kind of set your watch by. Okay. Once you reach that yield point and those bonds begin to break, we call that process, we call it dislocation. Those bonds have dislocated. That's when the material is, for a little bit, you know, from that 1 yard line to about that 10-yard line, that's when that material is freely deforming under that constant load. Now what's happening between here and here is those bonds, they're starting to sort of realign and sort of starting to figure out how can they begin to resist that load again. So once they've realigned and figured out how to resist load, they're going to kick back a little bit later into what we call this strain hardening region. Now, one thing I do want to mention is that once you get past that linear region in steel, and once you get into yielding, every deformation is permanent. It's a lot like the Coke can. Once you crush that Coke can, it's staying crushed, okay? But the nice thing about material behavior in this regard is if you take that load off and it unloads, like, you know, you've crushed it and then you let it go, it responds at that same slope. So if I load it up to here and let it go, it cuts back at that same slope. If I load it up to here, cut it back, it unloads at that same slope. So that Young's modulus parameter is a very constant parameter in the behavior of steel and in the behavior of many, many materials that we use in engineering applications. Now, one thing that you will find is that some materials don't have a well-defined yield stress. So, like, you know, for instance, steel has a very nice plateau region. We can say that's the yield stress. But for something like aluminum, that's not the case. However, knowing a yield stress or knowing an allowable stress is very, very important to us as engineers because it's one of the ways that we determine whether or not our design is efficient. I have a tension member, it's got some cross-sectional area A, and I'm putting 500 pounds on it. I take 500 pounds divided by A, and that gives me a stress. So I calculate 40 KSI. I compare that stress against what is allowable. So for steel, a very common allowable stress is the yield stress. But if I'm looking at aluminum or some other similar material, sometimes there is no plateau stress. So how do I figure out, bless you, how do I figure out what is the limit? Okay, so one of the techniques that we use in engineering is what's called the offset method. So if I have a material that has a very non-linear behavior to it, what I will do is I'll figure out what that slope is, and I offset it some. I offset it some value of strain. A very common offset value is 0.2% or a strain of 0.002. And so what I do is I take that 0.002 strain, I connect that up, and then whatever that value is right there, that's going to be my allowable stress. And that's a very common thing that you will see in engineering applications. So if you ever hear anybody say, well, what's the 0.2% stress or what's the offset stress, that's what we're talking about. It's when there's no nicely, no clear plateau or no clear yield stress, but we need something for engineering applications. We need something for design. So is everybody okay with that? Figure with that? Okay. Now, once those bonds have begun to realign after it yielded, some of those bonds begin to dislocate. Once those bonds have realigned and started taking load, it'll begin to deform again. It'll begin to accept load and resist that a little bit. And that'll happen until the material reaches what we call its ultimate stress capacity. Sometimes it's called its tensile stress capacity. So it's like the absolute maximum stress that an element can see. Once it reaches its ultimate stress, it begins to undergo a phenomenon called necking. The center of your tensile element area will start to shrink a little bit, and then you'll see it fracture. Now, if you're wondering why the curve sort of trails up a little bit, I'll explain that very easily, or very simply. I'm not going to expect y'all to do any math behind this, but I want to explain the difference between these two curves. The difference between these two curves is what's called engineering stress strain versus true stress strain. So when you compute an engineering stress strain curve, you're taking the stress divided by the area and the change in length divided by, or the force divided by the area and the change in length divided by the original length to get stress and strain. But think about those calculations. It's the change in length divided by the original length, and it's the force divided by the original area. See, here the area is changing, okay? So a true stress strain curve tries to take into account that the area is changing as well. So that's why, if you're looking at actual true stresses, the stress goes up like crazy. But for engineering applications, we more or less never really worry about that. So if you're wondering why the curves diverge, it's because the true stress strain curve is trying to account for the change in area and the change in length throughout the test. We don't need to worry about that for our purposes. Just wanted to throw that out there. Now, again, the benefit of a stress strain curve is that it is unique for a given material. If you have a different size bar, a different length bar, different what have you, you'll get the same stress strain curve, plus or minus, statistical noise and whatnot in your test, you'll get the same stress strain curve. Okay, and yeah, this is the difference between the engineering curve and the stress strain curve. So like I said, I'm never going to make you do true stress strain. Don't worry about that. It's only going to be engineering stress strain in this course. Everybody okay with this? Okay. So what I've got here is I've got a stress strain curve, and before we get into this example, I should preface this with the chili pepper from the Mexican restaurant because we are going to use a little bit of calculus in this problem. Oh no, don't worry, it's not too bad. I have here a stress strain curve, and this stress strain curve is defined by a function. Okay, so an engineer gave us this equation that would tell us what the stress strain curve is for a given material. And the engineer told us that's valid from a strain of here to a strain of here. All the stresses are in KSI. For this problem, I might be a little loose on the units because strain is unitless and stress is in KSI, so all my stresses are going to be in KSI anyways. I don't have to really get super nuts about worrying about unit conversions because there really aren't any on this problem. What I want to do is I want to plot the stress strain curve. I want to determine a theoretical modulus of elasticity, and I want to determine a 0.2% offset. Now, just so you're aware, I've gone ahead and given you in your slides, like that's the stress strain curve. That's going to be what it looks like. But I want to generate this in Excel, bless you, and I want to go through some of the math. So first off, let me close this real quick. Go away. All right. So I have here an Excel sheet, and I'm going to sort of just put this over here so that I can see what's going on. Let's calculate some quantities here. Now, like I said, I've blown the text up pretty big, so you should be able to read what's going on. All right. I want to have two columns right here, so we're going to have a strain column and a stress column. And the stresses are in KSI. Now, on the problem, it states that the strain, or this curve is valid from a strain of 0 to a strain of 0.03. So what I'm going to do is I'm going to say, all right, let's start off with 0, let's say 001, 0.002, and then I can take this. Forgive me if I'm going too fast, but let me know. So I know those of you who had me for computations, I know we did this in there. I can highlight this region, and remember that little cursor there on the bottom, and the plus sign turns to a thinner black plus sign right there. I can grab that and drag, and it'll continue that pattern. Y'all remember that? Been a while, right? Everybody remember that? Okay. So there's my strain values, which, by the way, when you're doing a stress strain curve, make sure and always have a value at 0. And that might be something to mention on the homework. I'm not sure if the homework had a value at 0. So, all right. So another way you can do that is you can say equals the top cell plus like 0.001 and just copy that down. You know, what have you. It doesn't really matter. So. Everybody good? And if you got a question, please feel free. I mean, you're not going to, you know, you're good. All right. Y'all good? Y'all good? I mean, if you got a question, I mean, please. Yeah. Okay. No, I mean, go ahead. I mean, you know, if you, I guarantee you, if y'all have, there's probably, you know, other folks having it. It's fine. Yeah.
So did you get from, like, how did you stretch it all the way to, like, 0.00?
Okay. So what I did is this. All right. So I started off with, I just typed in a value like 0.001 and like 0.002. Then what I did is this, okay? So I highlighted the region, like just like use the, you know, just sort of highlight all those, okay? And then look right here, okay? See how that turns from a white cursor to a thinner black one, see that? That's when you hover over that little corner on the bottom. And so just click and hold and drag. I promise I'm not going to be that professor because I'm not going to do that. Okay. So there's the strain, and then as for the stress, I'm just going to use this equation. So watch what I'm going to do. I'm going to say equals, I'm going to do the value over here on the left, so I'm going to say 17,500 times the strain divided by, and then I got to use parentheses, 1 plus 240 times the strain. Okay? And I just do that for the cell on the left. Okay? Now, when you do that, there's two ways that we can fill the remainder. We could copy and paste, like we could copy that cell and just paste it all the way down, or we go to that little square right there and we double click. And bam. Sound good? Now, for the sake of discussion, I want to plot this. I want to see what it looks like plotted. Okay? Now, I've got X data and Y data. Okay? So in order to plot this, I'm going to use a scatter plot. Okay? So what I'll do is I'll go up top here where it says insert. So right up here where it says insert, I'm going to say insert. And then I've got a whole bunch of charts, right? I've got bar charts, line charts, and all this stuff. It would seem that you would plot a line chart since you're graphing a line, but line charts only use one data set. We need X, Y data. So I'm going to use this one with the points, the one right there. And what I'll do is I'll click the little drop-down arrow next to it, and let's do the line one, like scatter with straight lines. Now when you do that, it's empty because it doesn't know what to plot. Okay? So what I'm going to do is I need to pick some data. So I'm going to hit this select data button right there. So select data, and then we got to add some data to the chart. Now, when you plot this, strain goes on the x-axis, stress goes on the y. So when I click my x data, so it says series x values, click that button right there, and just highlight all of these. And then for the y data, highlight all of these. Okay. And you should get something that looks like this. How are we doing? I mean, if you got questions, please. Yeah, this is time. Everybody good back here? Yeah.
How'd you type in the formula for column B to get it to generate?
Okay, so did you do the first one? Like the first cell right here. Did you get that first cell?
I just have 0.
Okay, so delete that. Okay, and then just start off by typing equals. All right, and then here I'll hover over the cell. This is what I typed in, and I typed, you know, everything's referencing to the cell next to it. So like this formula will say A6, this formula will say A9. Y'all get back here? Again, if you got questions, I'm not going to go. I'm the easiest guy in the world to get along with, believe me.
So for the graph, you just highlight both sides and just graph so far?
You can do that too. You can do that too. But I wanted to show the different data sets because I'm going to add something to this here in a second. Yeah, I wanted to show the hard way because you'll see why here in a second. Those folks that got a laptop, I want to make sure we're all getting this. You got this? You got this over here? Okay. Now, before we move on, and this is something y'all are going to have to do on your homework assignment, I do want to pretty this graph up a bit. So if you highlight the graph in Excel, see how there's like a couple of option buttons over here on the right? I want to click this plus sign where it says chart elements. And one thing I want to check is axis titles. So if you check that, you'll notice that I've got some axis titles here, okay? So I want to indicate that this title, or that this chart, has strain, and this chart, or this axis has stress. Anything else I should put on this axis? Well, I do need a chart title, but what about for stress? There we go, units. Why didn't I put any units on the x-axis? There are none, yeah. Okay, you can put inches per inch if you want, but I don't think it matters. And then for chart title, we can put, you know, example 4, you know, something like that. Not too bad, right? Pretty simple and pretty straightforward. Okay, so far so good? So is everybody okay on the plotting aspect? Okay. Now, let's look back at the example because I do want to go through the example and make sure that we're clear on a couple things. Now, plot the stress strain curve, okay? Then it says determine a theoretical modulus of elasticity. Bless you. Okay? So remind me, what is the modulus of elasticity? Like, tell me what it is. What? It's the slope of that line, and so you're looking ahead a little bit. Remember, it's the slope of that linear region, right? The problem is we don't really have a linear region on this curve. It doesn't really exist, okay? All we've got is this nonlinear curve. So why don't we do this? Why don't we try and, oh God, I don't know what happened there. Okay, that's weird. It's like off to the side. Let me do it here on the image here. So what I'm getting at, why don't we try and do this? Why don't we try and determine what the slope of the line is right there? Try and determine what that linear slope is at this region. Now, how do you find the slope of a curve? Take the derivative, right? So we're going to take the derivative and plug in 0 and figure out what the slope is right there. So let's break out our calculus, skills, and let's see what we can come up with. Remember, be safe. Please don't drink and drive. That was a very corny joke. Okay, so we've already plotted the curve, so let's look at our E value. So our stress equation is 17,500 epsilon, and I'll try and write the epsilon a little curly so everybody's with me on that, 1 plus 240 epsilon. So by the way, that's epsilon, that's a lowercase epsilon for strain. This is a lowercase sigma for stress, so everybody's aware of that. Okay, so what I need to do is I need to determine the derivative of that. So the derivative of that. Now, just so you're aware, this is probably the most challenging derivative we'll do this entire semester. So after today, you can relax. It's a lot easier from here. So how do I do this? The quotient rule, right? Oh man, this is bringing it back. Now, I'm gonna make this a little easier. I'm gonna factor out the 17,500. Okay. So how do we do this? We take the bottom times the derivative of the top, which in this case is just epsilon, right? Minus the top times the derivative of the bottom over the bottom squared. Is that about right? I thought we were good, we did this in Calc 1. We don't need to do it again. Don't worry, it's not that bad. Okay, so what's the derivative of epsilon going to be? 1. Okay, so 1 plus 240 epsilon minus epsilon. And what's the derivative of this going to be? 240. So that fraction, what do we got on the top? So we have 1 plus 240 epsilon minus 240 epsilon. 1. So 17,500 divided by that, that's our answer, right? So if I say 17,500 divided by 1 plus 240 epsilon squared, that's our answer, right? Sound good? Okay, so what is our E value? How do I determine E? What do I do? The Young's modulus, yes. Let me use the term. How do I determine Young's modulus? What value do I plug in? And what's the epsilon value? 0, right? Remember, we're trying to determine the slope at 0, right? So we take the derivative and we plug in 0. So if I plug in 0, what do I get? Exactly. So therefore, E is 17,500 over 1 plus 240 times 0 squared. And that's going to give me 1 squared on the bottom, which is 1, which is 17,500. Now, if you want units, what are the units of E going to be? Think about that. remember, here's our relationship. Our relationship is this equals E times strain. So what are the units of strain? They're unitless. This has no units, and this has to be in stress, like KSI. So what's this? KSI. So our E value is 17,500 KSI. Is everybody okay with that? Everybody okay with that? Let me show you something. Let's go back to Excel. All right? Let me move this over here onto the side. Okay, watch this. Let's add some data. Okay, so I'm going to start off with 0, 0. Okay? Now watch what I'm going to do. I'm going to pick a strain value. I'm just going to pick something. Okay? Let's pick, I don't know, this. Let's pick 0.005. You're going to see it doesn't really matter what value we pick here. Let me highlight this. Okay? I want to determine what the linear relationship would be. So what did we say the slope of the line was? What did we say, 17,500? So times that. Okay? So whatever this is. Okay? All right? Watch this. I'm going to go to my chart, and I'm going to select data, and I'm going to add another curve. So let's add another curve, just like we did before. My x values, those 2 points. My y values, those 2 points. Look what we got. Exactly what it should look like, right? Hugging that line. Let me go in here and let me play around with this a bit. I'm going to go into my axis. So y'all follow along with me. I don't like the way that my curve has stretched, so I'm going to go right-click here and hit Format Axis. And instead of going from 0 to 100, I'm going to go 0 to 70. Put that back the way it was. Sound good? So does that look right? Like that looks the way it should, right? Sound good, right? Okay. So far, so good? Now, before we do any math associated with solving for the last component, I want to show you something. All right, let's go back to our example. You can go away. All right, so we got to do 3 things with this example. We got to plot the stress-strain curve. We got to determine a theoretical modulus of elasticity, and then we have to determine this offset stress. Okay? Now, let's take a look at how we would do that. All right? First off, let's go here. We've got this plotted in Excel, right? And we've got this line right here plotted in Excel, right? Okay, so what are we going to do with the offset line? Our offset is 0.02%. So what would we do to this line? We would move it over, right? We would move it over how much? 0.02%, right? So watch what I'm going to do here. All right, see my curve here in Excel? Watch this. I'm going to set up a new column right here. Let me delete this. All right. So this right here corresponds to that orange line. What I want to do is I want to see what happens if I move this over. So how I'm going to do that is I'm going to keep my stress values the way they are, but I'm going to take my strain values and I'm going to add 0.2%. See what I did? Now, let me graph that line. So go to my curve, design, select data, and I'm trying to say what I'm clicking. So if you all watch the video, you'll see what I'm doing. I'm going to add a legend series. My X points come from here, and my Y points come from here. See what I did? So that point, that line moved over 0.02%, or a strain of 0.02, right? Make sense? Okay, so graphically, and let's take all the equations and the math that we're about to do off the table. What should our answer be? Like just looking at the curve, what should it be? What, like 36, 35, something like that? Y'all see that? So this is 30, this is 40. I'm going to guess something like 36, something about like that. So that tells me when I do my math, if I don't get an answer that's something like 36, what have you, then I did something wrong. Make sense? Everybody okay with that? Okay. All right. If you're okay with that, now let's do some math. Okay? Now, in order to do that math, what we're basically going to be doing is finding the intersection of two curves. So we're going to set these two curves equal to one another and solve. Okay? Now, we know the equation of the blue curve. Like we were given that. That's this. We know the equation of the blue curve. We need to know the equation of that, right? It's a line, isn't it? Equation of a line is what, y equals mx plus b, what have you? Now, what do we know about this line? Do we know the slope of this line? Yeah, it's 17,500, whatever, right? What else do we know about the line? We know that point, don't we? That point is 0.2% on the x-axis, 0 on the y. So here's what I'm going to do. Okay. So let me get a new sheet here. Okay. All right. So all right, so we got equation number 1. Okay, equation number 1 is sigma is 17,500 epsilon 1 plus 240 epsilon. Okay, that's equation number 1. Okay, what about equation number 2? All right, well, we have the slope. Well, here, let me do this. Slope is 17,500. Our point is 0.0020, right? So, and I'm going to do this in y's and x's because I think that'll be familiar. So y minus y1 equals m times x minus x1. I'm bringing it back, aren't I? All right? So y minus 0 equals 17,500 x minus 0.002. So y equals 17,500 minus, what is that?
35.
35? So another way of writing that is, or sigma is 17,500 epsilon minus 35. Is everybody okay with that? That's just, remember, sigma's on the y-axis and that epsilon's on the x-axis. Does that sound good? So here's equation number 1, equation number 2, set them equal to one another. So therefore, set those two equal to one another. All right? At this point, it should be a little bit of algebra. So let's see. Right? So take that denominator, multiply it over. What do I got to do over here on the right? A little bit of foiling, right? First outside, inside, last, right? So the first, we have 17,500 epsilon. The outside, what do we got for the outside?
48,960.
I got a second on that? Inside, we got minus 35, and the last we've got, what do we got for the last? Or did I get a second on the first one though? On that 48,960? I know it's early, I know. Making y'all break out the calculators. I know there's a couple of you that are like, so I didn't bring mine today. About that. I see. Shame. We doing good on the 48,960? Are we not? All right, well, all right, hold on. Okay, all right, hold on. All right, so the front one is 17,500 epsilon. The outside, what are we getting? 4.2 million even. So 4, like that? Is that right? Okay. The inside, that's minus 35. And the last, what are we getting for the last? 240 times 35. Say it again. 8,400. Do I have a second on that? Okay. All right. Can I cancel anything? What do I got on either side? Like if I subtract 17,500 epsilon from each side, that's going to cancel, right? So what am I going to get? I'm going to get 0 equals 42 or 4.2 million epsilon squared minus 8,400 epsilon minus 35. I don't know about you, but suspiciously to me that looks like a quadratic equation. Right? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You're like, it's 8:45, dude. Are you kidding me? It is too early for this. It's never too early for the quadratic equation. Come on now. All right, so do you all have the ability to solve this in your calculators? Usually, I know that those of you who took me for 111, I know that we covered this with the Casio. You're like, I remember, but man, it's been too long and it's too early. Now, so let's solve this out. Let's see what you get. Now, before we do that, let's recognize what are we solving for, a stress or a strain? We're solving for a strain. So what are we going to get? Some really small numbers, and that's okay. That's okay. So you tell me what you get. We're going to have two answers. So epsilon sub 1, epsilon sub 2. I'll help you out. I'll give you the first one. One of them is negative 0.00417. There's one of them. You give me the other. Negative? Yeah, I'm getting I got a positive 0.406 or 0.00406. Did you get that? You got 2-1? Hold on. Let me check something. I have my calculator on here. These? Huh. This is negative 0.0021. But this one's 406, right? That one's correct. Okay. I promise I'm not going to I have a mistake. I'm not going to take my eraser, throw it, and leave the room. I'm not going to do that. You're like, that's never happened in any of my classes before, ever. All right, so are we good on this? We good? Is this one right? Okay. Now, we've been arguing about the negative one, but the negative one doesn't really matter, right? Because ultimately, what we're after is where these two intersect, and we don't care about the negative one. We only care about the positive one. Now, what's the positive strain that you're getting? You said, what, 0.00406? Is that what you said? Is that right? Going down? That's about there, right? It's about where it should be. So is that our answer, though? No, we want to know what the stress is. So what do I do? I've got this strain. What do I do with it? Plug it in. Which equation do I plug it into? It doesn't matter, but I would plug it into Hooke's law because that one's simpler. That's just a line. So it doesn't matter which equation you plug it into, but I would plug it into the simpler one. So I would utilize this strain and therefore go to equation 2. So equation 2 is sigma is 17,500 epsilon minus 35. 17,500 times 0.00406 minus 35. And what do we get when you plug that in? You tell me. $36.05. Do I have a second on that? And so that's KSI. Does that seem right? It does. I mean, look at the curve. The curve said it should be right about here, somewhere about in the 35, 36 range, That looks about right, doesn't it? Here, I tell you what, if you really want to have fun with it, look at this. I'm going to go to Excel and see how I edited my axes to be 0 to 70. Watch this. I'm going to edit my axis to be 30 to 40. Okay? And so you can see, if you look 30 to 40, if you zoom in, you can see it's crossing right there around 36, So that's what we should have gotten, and that's what we got, right? Not too bad, right? Pretty simple. What do you think? I know we exercised some calculus and some math skills that you haven't used since 7th grade or 9th grade or what have you, but what do you think? Got any questions? Broke out Excel for the first time in a long time, right? Now don't forget, everything that we've done on the screen, everything's recorded, so if there's something that you missed or if you have any questions, you can go back to the recording and whatnot. Sound good? All right. What I want to do for the next couple minutes is I kind of want to introduce, oh, there's the eraser that I threw down on the ground. Yeah. I think Marshall University policy states I'm allowed to make 7 mistakes per semester, but then again, I'm the one that's tracking the mistakes, so it doesn't really work out, does it? That was another joke, not a very funny one. I do have a couple material parameters I want to discuss, and then I want to lay the ground for what we do next time. So I have here a little animation that I think is going to describe visually much better what I can do verbally. So when you apply a load and you stretch something, 2 things happen. Not only does it get longer, but more often than not, it gets thinner, okay? Now there is a relationship between what happens when something gets, that relationship between its lateral strain and its longitudinal strain, and we call that relationship and that parameter Poissons ratio, okay? Now, if you want an equation, here's your equation. We take the lateral strain and we divide it by the longitudinal strain. But there's a negative in there. Why is the negative there? Well, if I stretch something, it gets longer this way, but it gets shorter this way. So it's like we have positive strain this way, but negative strain this way. So if we were to just divide the two numbers, we get a negative number. So we throw a negative in there to keep everything positive. Here's some examples for Poissons ratio. For structural steel, we tend to use a Poissons ratio of 0.3. Concrete, it's common to use something like 0.2. And there's a couple different values. And Appendix I in the textbook lists a whole bunch of Poissons ratios for different materials. That's something worth mentioning. A couple other things worth mentioning. So Hooke's law, we typically, when we've been talking about Hooke's law, we've been talking about normal stress and strain. So normal stress and the normal strain applying that way. If you're talking about shear stress or shearing strain, there is a similar constant. Instead of the elastic modulus, we call it the shear modulus. So the elastic modulus we call E, and then the shear modulus we call that G. Now, there's an equation that you can use to actually compute G, and it's this right here. Just believe me on that one right now. We can derive that later, but for now, just trust me that that works. So if you take E divided by 2 times 1 plus this times Poissons ratio, you'll get the G value. You'll get the shear modulus. So just trust me on that. I promise it works. Okay. Another thing that I do want to mention is the concept of a factor of safety. So going back to our stress-strain curve, let's say we're talking about steel or we're talking about a yield stress. Well, if we're talking about regular old A36 steel, the actual yield stress is 36 KSI, which means if I go down to the lab and I take a piece of A36 steel and I load it and I break it and I start looking at the curve, its yield stress is 36 KSI. That is its actual yield stress, what I will actually apply to it to cause yielding. Now, there's a difference between what the actual yield stress is and what I'm calling the allowable yield stress. In simple terms, the long and short of it is this. So the allowable might be, I'm trying to think of the easiest way to put this, and maybe I'm throwing my terminology around a little differently, but I want to explain the concept and then I want to explain the math. So let's say it yields at 36 KSI. Maybe as the engineer, what I'll say is, no. I'm not going to use 36 KSI as the limit. I'm going to use 18 KSI as the limit. And in that scenario, what I've done is I've used a factor of safety of 2. I'm basically putting my limiting stress, I'm cutting it down a little bit to add some safety. Now, that's one way of thinking about a factor of safety. Another way of thinking about a factor of safety is through this equation here. The allowable stress might be the absolute maximum stress that you are allowed to have before you have deemed this element to fail, and the actual stress is what's actually on it. So let's say the allowable stress on an aluminum bar is 20 KSI, and you do all your math and you find that it's actually seeing 5 KSI. Well, in that case, the factor of safety would be 4. Now, one question I always get right around time is, what's a good factor of safety? And that is a good question. It's a great question. And there's no one answer, okay? What I mean by that is this. The first thing that matters is material characteristics. So certain materials are going to have more consistent behavior than others, okay? I think a fair way of characterizing it, at least for civil engineering, would be the difference between how steel behaves and how concrete behaves. Steel is produced through a highly controlled process, and you can pretty much set your watch by its behavior. But concrete is prepared in batch plants on, County Route 20 and whatnot. And I'm not saying that they don't have policies and procedures and specs to go off of. They certainly do. But just because of the variability of how concrete behaves, how it's placed, voids and whatnot, there's going to be a little more uncertainty with concrete than there is with steel. And that's the case with a lot of materials that we utilize. So there's one there. Another important point on factors of safety, which isn't really mentioned here, but is specifications. Some specifications will actually dictate to you this is the factor of safety that you shall employ when you're designing this type of system, and that's very common as well. There's also the idea of uncertainty and how we characterize that in engineering, but a lot of it boils down to engineering judgment. In short, the more uncertain you are about a scenario, the higher your factor of safety should be. What that factor of safety should be in what scenario, it depends. It's not that uncommon to use factors of safety of 3 or even higher in geotechnical engineering applications, because when you're designing a retaining wall or a foundation, soil properties are so highly variable that we end up bumping up our factor of safety like crazy just to account for that. Whereas, in structural engineering applications, we might use less of a factor of safety because we're more certain about how our elements are going to behave. So it just depends. There is no answer. I will say this for our class. One of two things is going to happen for this course. Number one, you're going to be doing a problem, and I'm going to ask you to determine the factor of safety. So I'll give you a bar, and it's got some load on it, and I'll tell you what the allowable stress is, and you determine what the factor of safety is. So you take its actual stress and its allowable stress and tell me whether or not it's safe, and if so, what's its factor of safety. So that's point one. The second thing that might happen is I might give you a factor of safety, and I might say, okay, if the factor of safety is 1.5, what's the diameter need to be in order to have a safe design? And so that's another instance. What I will never do in this course is say, design this bar, pick something for a factor of safety, that's fine, because I'm not grading 16 homeworks that could all be right. Yeah, I'm not doing that. And two, I think our purpose in this course is to understand the concept. So I think in this course, it's important to have sort of a closed form answer to where we're all going to get the same thing. When you get to your open-ended design scenarios in your junior and senior year, then you can start dealing with open-ended concepts. But in here, I think we need to keep it a little closed form. So it's never going to be that open-ended when it comes to this. Any questions? Any questions moving forward? Okay, so that pretty much covers what I'll call the fundamentals in this class. That's the fundamentals. If you understand stress and you understand strain and you understand their relationship, that is the fundamental material for this class. Okay? And so what we're going to do from here on out for the next little bit, quite a little bit, is we're going to start taking particular scenarios in civil and mechanical engineering and start exploring their behavior. The first thing that we're going to do is we're going to look at elements that are being subjected to axial load. In other words, they're being pulled on, they're being pushed on. And so that's what we're going to spend the next few days on, is axially loaded members, taking something and yanking on it. Okay? And we're going to handle all sorts of different scenarios with axially loaded members. We're going to talk about what happens when you take a member and you pull on it or you push on it. What happens when you take a member and you heat it up or cool it down? How does it behave then? We're also going to talk about indeterminacy. What happens if you have too many forces to solve for and not enough equations of equilibrium? For those of you in structural analysis, we've touched on that idea, but we haven't really dealt with it. Well, we're going to kind of deal with it in here on a member-by-member basis. In structural analysis, it'll be a system-by-system basis. And so axially loaded members is going to be one of the first things that we deal with. The next thing that we deal with are torsionally loaded members. What happens if you take a member and you twist it? How does it behave? And how a member behaves when you twist it versus when you pull on it, well, it changes quite a bit. And so Those different scenarios are going to be very important to us for the next quite a little bit. So we'll take axially loaded members first, and we'll start that on Thursday. Just to give you a little bit of a taste, what we're going to do is we're basically going to take the three concepts that we've been exploring over the past few days, the concept of stress, the concept of strain, and the fact that they're related in the linear range in order to determine deflection. If I yank on a member, how much does it deflect? And that seems pretty simple, and we're going to do some examples on that, but I'm going to ratchet it up a bit by asking, well, what happens if the load changes? What happens if the area changes? Okay? What happens if you have a tapered bar? How do you handle that? What happens if you have an indeterminate structure and what have you? And so that's going to be what we do for the next little bit. I'm going to close it there, end it about 5 minutes early because I don't want to get too heavy into material. Next time is, let me say this before we leave. Next time is the last day that we have in class before homework 1 is due on Tuesday. So next time we meet is the last time you will have a chance in class to ask questions about homework 1. So if you haven't looked at homework 1, I suggest that you do so that come Thursday, if you got any questions, that's the time to ask since I'm here and everybody else is. Sound good? See you on Thursday.